Section 3-3, Forecasting the Weather. Now, what you see on your screen right now is a standard weather station information set. This shows you pretty much all the basic weather information we need to know at any one location. The temperature is located typically on the upper left. We can tell by the numbers if it's degrees Celsius or Fahrenheit. If it was 57 degrees Celsius, we'd have record highs. So we know that this is in degrees Fahrenheit. This symbol off to the left of the circle is typically going to be for any form of precipitation, like fog, snow, rain. The different lines mean different things. Typically, the more they are, the more it is. So 3 circles represents heavy rain. The dew point is down here. Of course, that's going to be the same temperature scale as the temperature. Sky cover is inside of the circle, and that's kind of one of the easiest to see. If it's like half filled up, well, half of the sky is covered by clouds that day. Sometimes the pressure trend is shown, so this shows that the air pressure is dropping. That, however, is not on most weather station information sites, but the sea level pressure is. And we don't typically write out the whole sea level pressure. It's typically only the last couple numbers because that'll show us what's most important. And the last thing here is the weather is a little wind barb. This will go off of the main circle, show which way the wind is coming from. Not going towards, but from. We name our winds by where they come from. So this is pretty much a northeast wind. And these little pieces here on the end, they tell you how fast it's going. Typically, you can almost estimate about 5 for each half. So this is a full, so that'd be 10 and half here. But typically, you'd assume that'd be around 15. The numbers are off by a little bit, but it's pretty close to that. Now, these are the precipitation icons that you'll see on there. 2 seems to be the minimum, so 2 circles would be rain, light rain, moderate, and then heavy. The little asterisk symbols look like they're going to be snow. Here's thunderstorm with rain, with snow. Thunder, snow does happen. Here's no precipitation, which does happen from time to time. Rain shower, snow shower, drizzle, freezing rain has a little squiggly line. Ice pellets or sleet. Fog and haze are typically, these are more common than this whole section. So it's either rain, snow, or these here. So those are the ones to remember. Again, wind speed and direction shown by the symbol. It's always identify which way the wind is coming from, because that is how we name our wind. 1 knot, and that's typically the measurement we'll use, is about 1.15 miles per hour. So it's pretty much about the same. So here you go. Half is 5 knots, a full is 10, a half and a full is 15, and then you see 20. And we can keep doing that. 50 is going to be this little triangular shape. So this one here will be a northwest wind, and that's 10, 20, 25 knots. We use a range. So the first one would be, just a line would be less than 5. Half a line would be like 5 to 9. And the full line would be 10 to 14. With miles per hour, it's just going to be about the same, just slightly a bit different. Pretty much we just want to use this if we're talking about a high wind or a low wind. And then sky cover. This is by far, I think, one of the easiest ones to pick up because if it's clear, no clouds, if it's all the way filled in, completely overcast. And then you see by how much we fill it up. You can see by how much it gets to 9/10. Mostly going to be full. A little gap in there because, well, 1/10 is just going to be the opposite of that gap. 2/10 or 3/10. You talk about quarter, really. This is between a quarter and a half, half, between a half and 3/4, 3/4, 9/10, and then completely full. Sky obscured mean that whoever recording the weather, which is typically we have automated weather stations which record all this, upload the information. We get that from all over the United States. So something may be covering the receiver at that point, so it can't give you information. So the X pretty much means no information about that. Now, information is the most important thing in making accurate weather forecasts. The more information we have, the better forecasts we can get. We have a tremendous amount of weather information available to us nowadays, thanks to computers and the internet. We have automated weather sites which are powered by solar panels, and they're placed all over the place, and they transmit the information up. We have weather balloons, we have satellites. All this combined has made so we have the most accurate forecast we've ever had. But they're still not as accurate as they can be because we're still dealing with a very difficult problem of predicting the weather. There are so many variables at work that even by knowing as much as we do know, because of how many variables it is, one little change here causes a big change down the road. That's often referred to as the butterfly effect, because butterfly flaps its wings in Argentina and causes a snowstorm in New York. And the whole reason is that the whole atmosphere is connected, so you see a slight change in one place can cause a big change somewhere else. Now, a forecast starts with your observations, cloud type and amount. That'll tell you if the air is stable. That'll tell you if there's a lot of moisture in the air. What is the temperature? What's the humidity? What's wind speed direction? So we start from that. We can use weather balloons, which are also called radiosondes. These are balloon-borne instruments that measure and transmits pressure, temperature, humidity to a ground-based receiving station. So we have the ground here, we have this big weather balloon, and then it's attached to a little box. And that little box controls all of our information. That's going to be all of our instruments are going to be in there. And it's going to transmit that data back to the ground because this balloon is going to rise in the atmosphere until it pops. And once that balloon pops, the data is going to come back down to Earth, and it's not going to be usable. So we need to transmit it while it's in the air. So it'll measure everything as it goes up. It includes the altitude. So we know what the atmosphere is doing at every little step, because what happens up very high can impact what happens down low. So here you see a picture of here's the weather balloon itself, and here, right there, that is the radiosonde. That's with all the instruments that will go high up in the air. Typically, you'll see a lot of labels on it, so if you do find one of these in a field, you can just put it in a mailbox or take it to the post office, and it'll get back to the researchers that use it. Some of these can be used again and again, but typically it's a one-time use thing. Radar. Radar is by far one of the most important tools to a forecaster, especially for immediate forecasts. If I want to know what's going on in the next hour or so. Radar is an electronic instrument used to detect objects such as precipitation by their ability to reflect and scatter microwaves back to a receiver. They can measure size and intensity of precipitation, so we can know how big of rain droplets there are and how fast it's falling, how thick it is. We can also use this to identify storm position and motion. What we can do is we can take a picture of where the rain is, and then like a couple seconds later take another picture, and then another picture. And by adding those all up, we can get the generalized motion of a storm. We can see if it's growing in intensity or weakening. And it gives us some good understanding of if it's going to pose a hazard to certain towns or not. And this is a typical radar station. There's going to be inside of this dome, there's a transmitter. So you almost think like a satellite dish. And it's going to be sending out these signals. Now the thing is that they travel at near the speed of light, which is 300,000 kilometers every single second, or about 180,000 miles every second. So these things travel very quickly, and then they get reflected back, and by the intensity, how quickly they're coming back, we can tell a lot about what it hit. And so we're trying to identify rain droplets in the atmosphere. Now, Doppler radar is kind of the newer version of radar, and we even have a newer version than that, typically what's called NexRad. But we use the Doppler principle, which is if you ever heard a siren coming towards you or away from you, you'll notice that the pitch or frequency of the sound changes. Same thing happens with the signals that we send to the rain droplets. If they're coming towards us or away from us, they'll actually change the pitch. So it'll be a higher pitch or a lower pitch, and we use that to identify if it's coming towards us or away from us and how fast. This becomes very, very important because when we're talking about one of our biggest weather phenomena, tornadoes, then that happens because of rotation in the cloud, and we can actually use Doppler radar to identify rotation, so we can tell if there's a tornado inside that cloud or not before we even have to see it with our own eyes. Radar allows us to see this, so it allows us to come up with a better prediction than for tornadoes. Satellites give us a tremendous amount of information. It's just a satellite that used to monitor weather and climate of the Earth. They see more than visible spectrum. They don't see more than cloud systems. We can detect city lights, fires, effects, pollution, aurora, sand, dust storms, snow cover, ice mapping, boundaries of ocean currents, energy flows. We can see visible light, which allows us to see the clouds. We can see infrared. We can see. We can focus on various specific wavelengths of light. Like we can look at the specific wavelength associated with water vapor, and so we can analyze all this. Now, typically, you either have a geostationary satellite, so geostationary, which means that over the Earth, there's only one spot that is always over. Or you have a satellite that has a path, and the path will change over time. And we use that to cover the whole Earth over a set period of time. Geostationary orbits are typically the ones we use because they can actually focus on like all of North America at once, They can focus on the Atlantic at once, the Pacific at once. And so I just need to go look at each satellite's the different information, but they do cover a ocean. But the biggest tool we use nowadays are computer models. Now, a computer model is a program that uses complex mathematical equations, information multiple sources, weather can predict the probability of precipitation, type precipitation, temperature ranges. It's going to spit out a diagram which says, okay, here are the chances for precipitation in these various areas. This is going to be the intensity. This could be the temperature ranges we expect. Computer models, of course, and here's the important thing, plural, because we don't have one equation that works. We have multiple equations that we combine together to try to get a more accurate view. So we have different types of computer models. And a forecaster may look at only a couple of computer models, or could look at more than 10 computer models to come up with their forecast. But it's the complex mathematical equations which were developed by looking at past information and trying to figure out what variables cause that weather to happen more often than not. But there are, again, so many variables at work, you have to look at almost the whole world at a time, that it does become very, very complex. And these aren't typically equations that are being carried out on a cell phone or even a small laptop. We're still using very, very powerful computers to calculate these models. Another useful thing is recent history, because you know what the weather was recently should be close to what's going to be. Weather doesn't change a whole lot from day to day. If today's in the 70s, I don't expect tomorrow to be in the 20s. So that does eliminate it gives me a smaller range to look at unless I see a big change coming in. So weather typically doesn't change a whole lot day to day. And we look at our climate. The average weather over a long period of time, usually at least 30 years. Not a whole lot of variance between years when you're talking about average rainfall, average high, average low. When is the first snowfall? When is the first melting? So climate does give us some understanding, but you cannot just look at climate. Things like the almanac, the Farmer's Almanac, look at climate. But that's not the only thing we can look at nowadays, because we talk about like this year could have been the driest year in a long time for certain regions of the U.S., or it could have been warmest, or it could have been the wettest. So the weather does vary from year to year, but it's still not going to change a whole lot from that climate. All of a sudden, Arizona is not going to see as much rainfall as we're going to see in the summertime. And then there's advanced methods. Again, prognostic charts, again, using our computer model, AWIPS, Advanced Weather Interactive Processing System, using a lot of information there. Ensemble forecast, where we combine all the forecasts together. Persistence forecast is more like what's been recently. It will be that. A steady-state forecast is a trend. It's getting warmer, it's getting colder, it's getting drier, stuff like that. There are a ton of methods that we go out to use to predict the weather. Now, one thing I want you to pay close attention to, let's say that the forecast for tonight said that there's a 20% chance of precipitation for tomorrow. Now, that doesn't tell you how heavy the precipitation, that doesn't tell you how long it's going to last. It just says the chance of precipitation in your specific area is a 1 in 5 chance, a 20% chance. Now, typically what that means is that 20% of the computer models predicted precipitation for that area. Or it could be a combination of other factors. I could have, like, let's say I'm looking at 10 computer models. 3 out of the 10 say there's going to be precipitation, but I also know a couple things about my area. And I know that under these conditions, there tends to be more rain than not, and so I may bump that up a bit. So from 3, you may go to 40 or 50%. If it's a 90%, or really 80% on up, you're going to get rain. If it's 20 or so, it can be scattered. So the higher percent means the more models are predicting it's more likely it's going to happen. We don't just say it's a 50-50 shot every day, because we have so much more information. We know if it's likely or not it's going to rain the next day. Yeah, sometimes we get caught off guard, but that could be because something changed we weren't expecting to change, or there wasn't one variable that we're paying close enough attention to. And so every forecast, we can look back and see how accurate we were, but can lead to a better forecast down the road. And that's what meteorology takes us to. Someday we'll have a very accurate forecast.